Hello everyone, my name is Eugene Kang and this is Lab 1 Constant Velocity for Physics 2211. So the purpose of this lab is to demonstrate Newton's second law by studying the motion of an object traveling at a constant velocity with both experimental and computational models. So for this experiment, I'll be observing the motion of a marker and I'll be observing that motion using a software called Tracker. And then after that, I'll be using a computational model using the software GlowScript to predict the velocity of the marker. The results of this lab were that the observed and expected velocities of the marker were similar, demonstrating the principles of Newton's second law. So before we go on to observe the data that we collected, it's important to define Newton's second law. This law states that the net force acting on an object is equal to its change in its momentum divided by a certain time period. This means that if the net force on an object is zero, then its change in velocity must also be zero. Using these three equations from Newton's second law, we can derive these and combine these into what is known as the velocity update formula, which we will use to observe the velocity of the marker in this experiment. So the procedure for this lab is as follows. First, we have to define the system as the marker and then define the table and the earth as surroundings. Next, we have to record a video of the marker rolling at a constant velocity. Then we use the software tracker to measure the marker's position over a time interval of constant velocity. Then we code a computational model of the marker's motion using GlowScript and the code template for this lab. After that, we plot the data of the predicted and observed models onto a single chart, comparing position over time, and then we compare both models and conclude whether it demonstrates Newton's second law of motion. So here is the video uploaded into Tracker. Using this software, as you can see, we can define the location of the marker at each frame in the video, and then we placed a meter stick next to the marker so that we know the relative distances. Using this software, we get a chart of data points and a graph right here. Using the data points we got from Tracker, we're now able to plot these data points and then figure out what the line of best fit is. And with this equation right here, we can plug it into GlowScript and get a second set of data points that will tell us the expected or predicted position over time. So we have an equation, but what does it mean? So that first number there is our average change in position per second, or average velocity, and the second number is our initial starting position. So along with the total amount of time passed, which is 1.06 seconds, we can plug all of those values into this script right here, which will use Newton's second law to constantly analyze the position and velocity of the marker for every 0.01 seconds passed. When that happens, we will be given a set of data points, which we can plot and compare to the observed data points. So now that we've ran the script, we can take those data points and put them on the same graph as the observed data points. Looking at the two lines, we can see that the observed line is slightly curved, but other than that are really similar. Because that observed line is so similar to the predicted model, which assumes Newton's second law to be true, we can also say that the observed line demonstrates that Newton's second law is true. So now that we know the results of the lab, we can ask some further questions. The first one being, what if the x-axis was flipped? Or in other words, what if the marker was going left to right instead of right to left, like in the original video? The only thing that would really change is the slope of the graph. It would flip signs, so it would be positive instead of negative, but it would keep the same magnitude and slope. Second question, is the net force zero? Are there other forces affecting the motion of the marker? Well, we can assume because the graph data points from the observational model seem to follow a different slope than the computational model, there are some other forces that cause the net force to not be equal to zero. That was the end of this lab report. Thank you for your attention.